In this video, we'll be talking about probability as a formalism for knowledge representation and inference in artificial intelligence. So the way that people think about artificial intelligence has changed a lot since the early days in the 50s and 60s and 70s. And probably the single biggest factor that characterizes that change is the turn towards probabilistic approaches. So in the first part of this course, we were mostly concerned with deterministic problems and certain information. So graph search definitely had this flavor. We knew everything that there was to know about the world, and we knew exactly what the outcomes of our actions would be. The only problem was to figure out what sequence of actions we had to follow to reach our goal. And logic definitely had this flavor too. So a formal language like predicate logic, it's very expressive. We can represent a huge range of natural language sentences. So we can say all dogs are furry. We can translate that into predicate logic and capture that meaning perfectly. But logic is really only good for certain information, for information that is either true or false. So there's some sentences that don't translate well, right? If I want to express the fact that most dogs are furry, or that this dog is probably furry, we can make some attempt to translate sentences like that into logic, but we're going to lose something in the translation. And if we can't deal with uncertainty explicitly, we're really losing something important. So, right, everything that we know about the world is uncertain. If I turn the key in my car, I believe that it's going to start, I expect that it's going to start, but there's some uncertainty associated with that. I could be wrong. I feel really confident that the sun will rise in the east tomorrow, but again, I could be wrong. There could be a giant spaceship approaching that's going to destroy the sun before that happens. That's a very unlikely outcome, but there's some uncertainty. From a more practical point of view, if I'm building some artificially intelligent agent, if I'm building a robot, the sensors for that robot will never provide perfectly accurate information about the world. There's always going to be a certain amount of noise and uncertainty in those sensor readings. And we can work really hard to engineer those sensors so that they're as good as they possibly can be, and we can drive that uncertainty down, but we can never drive it to zero. So we'll never have perfect information coming from the sensors. And similarly, the actions of that agent or that robot will never be perfectly reliable. So I can send a signal to the wheels and attempt to move the robot forward by exactly 1 meter, but inevitably I will fail, right? The robot is never going to move forward by precisely 1 meter, even if it's only off by 1/millionth of an inch or 1/millionth of a centimeter, it will be off. And that's in the case where everything works as it should, right? It's also possible that there's a loose connection or the motor's burned out and the robot doesn't move at all. So what do we do? How do we deal with the fact that our knowledge is inevitably uncertain? So there's a long history of trying to augment formal logic in ways to sort of deal with uncertain information. And I would argue that that's probably not the best approach. So what we really want is to build our methods of knowledge representation and reasoning on a foundation of probability theory. So there's a nice sentence in our textbook that sort of captures why that's a good idea, why that's the right approach. Let's see if we can find that. And it puts uncertainty and probability theory in the context of gambling. So probability is the calculus of gambling. When an agent makes decisions and uncertainties are involved about the outcomes of its action, it is gambling on the outcome. However, unlike a gambler at a casino, the agent cannot opt out and decide not to gamble. Whatever it does, including doing nothing, involves uncertainty and risk. If it does not take probabilities into account, it will eventually lose at gambling to an agent that does. This does not mean, however, that making the best decision guarantees a win. So the point here is that in fact, all actions are gambles, and it turns out to be the case that the right thing to do is to gamble according to the rules of probability. If you don't gamble according to the rules of probability, it can be shown that you're guaranteed to lose in the long run. So in that sense, it's just factually correct that the rules of probability are sort of right in the sense that if you ignore them, you will lose. You will do the wrong thing. So that's why we care about probability. That's why probabilistic approaches have sort of taken over in AI, right, in almost any practical problem, there's a lot of uncertainty, and the right tool for dealing with uncertainty, right, is this tool that's been developed over the last few hundred years of probability theory. So I've got some slides here that I've used in the past to talk about probability theory, and unfortunately they don't perfectly match the information as it's presented in our textbook, but a lot of the same ideas are there, so hopefully that won't be too confusing. Okay, let's start out by getting some notation down. We'll be dealing with random variables, and we'll usually denote random variables with capital letters, or they'll at least begin with a capital letter. And random variables may be Booleans, they may be restricted to be true or false, or they may not be. So we can even have continuous valued random variables, although we mostly won't talk about that today. We'll consider only discrete valued random variables. So P, right, is going to be our notation for the probability of some event, or the probability of something being true. So, and we'll use lowercase to represent particular assignments to our random variables. So in this case, P of A is the probability that this Boolean random variable A has the value true. Probabilities like this, that are just the probability of a particular event, are also going to be called unconditional probabilities or prior probabilities, and we'll see the alternative to that as we go. So I'm hoping that a lot of this is going to be review, that you've seen most of this in a discrete math course. So we'll go pretty fast, and we'll focus on sort of using probability in artificial intelligence. I put this slide up because I think it can be handy to think of, right, what do probabilities mean. It can be handy to think of them in terms of sort of set notation and drawing Venn diagrams, right? So when we talk about the probability of A being true, we can think of that as measuring sort of the percentage of the fractions of worlds in which A is true. So if we sort of draw this picture where the blue thing is every possible way that the world might be, this little green box is the fraction of those ways in which this variable is true. And then we might end up with something like, right, the probability that A is true is equal to 0.2. That's the area of this little green box. The probability of not A equals 0.8. That's the rest of the world, right, the blue that isn't covered by the red. We're going to generally be talking about the probability of propositions. So in general, right, we might say the probability of some proposition alpha, and that could be built up using our language of propositional logic. So we can ask about the probability that A and B are true, for example, and we'll often use the shorthand for, we'll replace an and with a comma. Or of course we could talk about the probability of A or B being true. And we can look at what some of those things would look like, given that sort of set view of things here. So the probability of A and B being true, right, that's this little box, this subset of possible worlds where A is true and B is true as well. So that overlap is A and B. A or B then would be any area here that's covered by either A or B, obviously, etc. So it turns out that you can sort of build up all of probability theory from a small number of axioms. These axioms are in the textbook, and I think none of them are very surprising. Maybe what's surprising is that you can do so much with so few. So the axioms are that the probability of any proposition has to be greater than 0. That makes sense, greater than or equal to 0. The probability of a tautology, the probability of something that is known to be true, is equal to 1. So that's what the probability of 1 means. And if two events are contradictory, if these are contradictory propositions, if we know that only one of them can be true, then the probability of A or alpha or beta equals the probability of alpha plus the probability of beta. So thinking back to our Venn diagram picture, that would be the case where there's no overlap between A and B, and the probability of A or B would be the sum of the size of those boxes. And we won't look at it, but there's a nice couple of pages in our textbook where he shows how you can build up from these axioms of probability 4 or 5 very useful identities Here's one of them. So if we wanted to show that the probability of not alpha, the probability of the negation of some proposition equals 1 minus the probability of that proposition, right? And this makes a lot of intuitive sense. If it's 80% likely that I'm going to win the lottery tomorrow, then it's 20% likely that I'm not going to win the lottery tomorrow. So this is something that we would all accept. And it follows from the propositions, right? I can use axiom 2 to say this, the probability of not alpha or alpha equals 1. So this is a tautology. It's definitely true that not alpha or alpha must be the case. And the probability of a tautology is equal to 1. Check. And then from there, I can go to this using axiom 3. So not alpha and alpha are contradictory propositions. They can't both be true. So that means that the probability of not alpha or alpha equals the probability of not alpha plus the probability of alpha. And then I can just rearrange these terms. I can subtract the probability of alpha from both sides, and I've finished my proof. I've shown that this identity is true. So I encourage you to look at the rest of the identities and their proofs in the textbook, both because it's nice to see where they come from, and because those turn out to be some pretty useful identities that he describes. This is just to point out that we're not restricted to using Boolean valued random variables. We can have random variables that can take on any number of values. So, for example, we might have a variable w that can take on the 3 possible values: sunny, cloudy, or rainy. And this is just to point out that the sum of the probabilities of those possible outcomes has to equal 1. Okay, so now things start to get a little bit interesting. We can talk about conditional probability. And this is going to be very interesting for us, right? Because what we're going to be interested in is sort of drawing conclusions from evidence. And the conditional probability, right, talks about what's the probability of A being true, or given that B is true. So given that we know B, how does that change our probability that A is true? And a sort of intuitive example here, right? Maybe if I don't know anything else, if I've been locked in a cave for a year and I don't even know that it's been a year, and I'm asked what's the weather like outside, I might say that the probability that it's sunny is 0.1. But if someone gives me some additional information, if I'm told, well, it's warm outside, then that's going to probably increase my estimate of the probability that it's sunny. So we can define the conditional probability in this way. So the conditional probability of A given B is equal to the probability of A and B over the probability of B. Let's see if we have a... So again, I think our picture sort of makes that make sense. I'm interested now, right? What is the probability of A given B? So to say that I'm interested in the probability of A given B is really saying I want to just look at the worlds in which B is true. So that's restricting myself to I'm throwing away everything except this little piece of the universe. And then I want to know, well, what's the probability of A given B inside just that little piece of the world? So then it makes sense that that's probability of A and B, right? That's the size of this thing, right? Over the probability of B. That's very pretty, right? Over the size of this whole thing. So if we know that the probability of A, for example, is 0.3, that's the size of this box. The probability of B is 0.1, that's the size of this box. And the size of their overlap, right, the probability that A and B are true is 0.05. Well, it doesn't matter anymore what the probability of A was, right? What I care about is how big is this overlap given the probability of B. So my answer is 0.05 over 0.1, right? 0.05 over 0.1, and that's 0.5. So if I don't know anything else about the world, my belief about the probability of A is 0.3. But if I know that B is true, right, that makes it much more likely that I think that A is going to be true, because then I'm just looking at this little region of the world. And this is also called the product rule, so we can rewrite this thing by multiplying both sides by b, and we end up with this. Okay, so we can talk about probability distributions. A probability distribution is just a complete description of the probability of all possible assignments to a random variable. So if our random variable is A, the complete probability distribution can be expressed this way. The probability that A is true equals 0.1. The probability that A is false is 0.9. Now we know everything there is to know about the probability of A. It'll look a little bit different if we have a random variable that isn't a Boolean random variable, right? So this, our weather variable from before, we would write its probability distribution maybe as a little a vector here, a little tuple. So sunny, cloudy, rainy are the three possible outcomes. 0.2, 0.7, 0.1 are the probabilities associated with those three outcomes. And notice that they sum to 1 and that these sum to 1 as well. So what's going to be a little bit more interesting for our purposes are joint probability distributions. So a joint probability distribution takes a set of random variables, a collection of random variables, and assigns a probability to every possible assignment to all of those variables. So, for example, if we have two Boolean random variables, what we end up with over here is sort of the truth table for those two random variables. Right? This is every possible assignment to those two random variables. And we'll end up with a probability for all of those possibilities. And notice that if we add all of those things up, they sum to 1. That's not surprising, right? One of these rows has to represent reality. There are no other possibilities, so they should all add up to 1. And they're all mutually exclusive, right? Only one of these rows can match the way the world actually is. The situation is the same if we have non-Boolean valued random variables. We just have more entries in our table for our joint probability distribution. So these are all of the possible ways that the world might be if we're interested in only these two random variables, the rooster crows and the weather. So the rooster may crow, rooster may not crow, and for every decision that the rooster makes, the weather could be in one of its three possible states. And it looks like the rooster never crows when it's rainy. So I've sort of probably mangled this a little bit. This is sort of torn from the notation that the textbook uses. What ultimately we're interested in doing is probably inference, right? So we want to know the probability of something given what we know about the world. So we have some information about the world and we want to draw conclusions about what must be true. So this is similar to the kind of inference that we wanted to do when we were working with logic, except now what we're interested in is not determining whether something is true or false, but what the probability of something is. And this is saying that we can figure out the probability of something by adding up the probability of all of the worlds in which that thing is true. And I think the best thing to do is just to show an example. So let's say I want to know the probability that A is true, and this joint probability distribution represents what I know about the world. So in a sense, the joint probability distribution is my knowledge base, right? If I have the joint probability distribution, that's sort of a complete description of the way a particular world works. I know the probability associated with every outcome. So if I have joint probability distributions, it turns out that inference is going to be easy. And we'll see in a few minutes that there are going to be some difficulties associated with having and working with joint probability distributions. But for a simple case like this, life is good, right? I want to know the probability that A is true. So all I need to do is find all the rows, all the worlds in which A is true. There's one here and one here. I add up those probabilities, 0.1 plus 0.3. And it turns out that the probability that A is true is 0.4. Oops, sorry, 0.1 plus 0.2 equals 0.4 equals 0.3. math was never my strong suit. There's a word for this adding up process. It's called marginalization. This is actually one of the identities that is proven in the textbook. And this is a little bit more of a general form. This is just saying that if I want to know what the probability of a particular variable is, I can add up across all of the assignments of all of the other variables, which is what I did here. More frequently, we're going to be interested in conditional inference, right? If I know that something is true, what does that tell me about some other thing? So here's that joint probability distribution we saw before about roosters and weather. So this is good. My joint probability distribution sort of tells me everything there is to know about this world. Now can I draw conclusions from that, right? So can I figure out what's the probability that the rooster crows given that it's sunny? Well, I can apply here my definition of conditional probability, which was this, if you remember. And then now I just need to figure out, well, what's this probability, and divide it by this probability. And I can calculate each of these by summing across all of the rows, all of the worlds in which these two things hold, right? So probability A and B. Probability that the cock crowed and that it was sunny. So I need to find all of those where those are both true. Looks like this is going to be the only one. So 0.05. Then I need to look at all of the rows, all of the possible worlds in which it was sunny. So there's that one there, and then there's also this one here. So 0.05 plus 0.05. Cool. So it looks like this is going to work out to 0.5. It's 50% likely that the cock crows if the weather is sunny. All right. So I've said that the joint probability distribution is really important and really useful, and we've seen a couple of examples where we can answer inference questions by referring to this joint probability distribution. In fact, we can answer basically any question, any inference problem using this joint probability distribution. So that sort of raises the question of where we get one of these joint probability distributions. We can make it up, right? So if we think we know a lot about some domain, we can fill in those probabilities in accordance with what we think we know. We've been talking about machine learning, so we can also learn this. In this case, learning just means looking at examples of worlds and counting which of those worlds fall into these different categories. So for example, I might stand in the barnyard for, say, 38 days, and with a sheet of paper and write down on how many of those days the cock crowed and it was sunny, and how many of those days the cock crowed and it was cloudy, right? For every one of these possible outcomes, put down a tally mark. And these are all mutually exclusive, right? Only one of these rows can be true on a particular day. And then I can, for each entry in my joint probability distribution, I can just divide the number of times I saw that particular outcome by the total number of days that I observed, and that'll give me an estimate of the probability that event. And assuming that a stationary world in which the sort of physics of roosters and weather doesn't change, and assuming that I sort of keep gathering this data infinitely long, these estimates will eventually converge to sort of the true probabilities of these events happening. So any problems? There's actually a huge problem. There's a glaring, enormous, serious problem that I've been hiding from you up to this point. And that problem becomes more clear when we think of, what's going to happen if I add another variable to this domain that I'm interested in here, right? What happens when I add, say, the temperature? Is it cold or is it hot? Well, that's going to double the size of this joint probability distribution table, right? I'll have to have all of these possible entries for days on which it was cold, and I'll have to have all of these possible entries on days for which it was hot. And in general, every time I add one more Boolean variable, that doubles the size of this joint probability distribution. This is the same problem we had before when we were trying to construct state spaces for search problems. Right? Every time we wanted to add a new piece of information to our state space, that made the state space twice as large. So this is a problem, right? We can't have exponentially large probability distributions and store them in this explicit form. We would run out of space on the computer, and we can't gather enough evidence to fill in such a enormously large probability distribution table, right? So if I have 20 Boolean random variables, the size of my table is going to be 2 to the 20, which is roughly 1 million entries. So it takes a lot more than 38 days to gather enough evidence to sort of get reasonable estimates for all 1 million of those entries. Most of them won't happen ever over the course of those 38 days, right? So I wouldn't want to conclude that the probability of those outcomes is 0 just because I haven't seen them yet. So this is a serious problem. This is the problem of probabilistic inference. So how are we going to deal with it? And the solution, to the extent that there is a solution, turns out to be this notion of independence. So if you have 20 variables, if you want to explicitly represent the joint distribution over those 20 variables, you're doomed. But lots of those variables actually probably have nothing to do with each other, right? So if we're interested in whether or not the cock crows, and we're also interested in whether it's a Wednesday or a Thursday, those two pieces of information probably don't impact each other at all. Knowing one doesn't help me to make predictions about the other. And that's exactly the notion of independence, right? So here's our definition of independence. A and B are independent if the probability of A given B is equal to the probability of A. So basically that's just saying that these two facts, A or B, have nothing to do with each other, right? If I have some belief about the probability of A, and you tell me B, and that doesn't change my belief at all, right, then those two facts are independent of each other. Right? So, remembering our product rule, this can also be written this way. A and B are independent if the probability of A and B is equal to the probability of A times the probability of B. So this turns out to be basically the trick for avoiding filling out that giant exponentially large joint probability distribution table. We'll take advantage of the fact that lots of the variables are independent in order to be able to very concisely represent very large probability distributions. And we'll see more of that as we go along. So one more incredibly useful identity, probably the most useful identity in artificial intelligence, Bayes' rule. So we'll have to unpack it a bit to figure out why it's so immensely useful. It doesn't look that way on the first glance. So we'll interpret here H to be hypothesis, something that we want to know whether it's true or not, or something that we believe might be true. And we'll interpret this E to be evidence, some piece of information, coming from a sensor, or some piece of information that we've been told. So Bayes' rule tells us that the probability of our hypothesis given our evidence is equal to the probability of the evidence given the hypothesis times our prior probability of the hypothesis over the probability of the evidence. Okay, we'll see in a minute that makes sense and that it's helpful. And there are words for some of these terms. This probability of the evidence given the hypothesis, the name for that is likelihood. So this whole thing can be rewritten this way. We could say that this is a posterior probability. This is the probability of our hypothesis after we've seen some evidence, is equal to the likelihood, the probability of the evidence given the hypothesis, times the prior, right? This is our prior probability of the hypothesis over the evidence. So, right, generally what we want here is this, right? We're interested in knowing what the probability of our hypothesis is. And it doesn't immediately seem that this identity is going to help us, right? Because we wanted one probability, And in order to calculate it now, we need 3 additional probabilities. So how does that help to go from not knowing 1 to not knowing 3? Well, it just turns out that often these 3 probabilities are easier to get our hands on than this 1 probability. So a common example of how you would apply something like this is in like medical diagnosis. So let's say our hypothesis now has something to do with the disease that a patient has. So in this case, we're interested in the probability that a patient has pneumonia. These should be evidence. Evidence. And our evidence represents some information about the symptoms that we are observing in this patient. So it turns out, right, that we sort of know what pneumonia does to people, right? We understand the causal relationship between pneumonia and the symptoms that we observe. So it's easy for me to know that the probability of someone having a cough if they have pneumonia is 0.5. Almost everybody who has pneumonia has a cough, or half the people who have pneumonia have a cough. It's harder to sort of know in advance the probability in the other direction. So what's the probability that someone who has a cough has pneumonia? That's hard to say because people can have coughs for all kinds of different reasons, right? So does it mean they have pneumonia or not? Well, we don't know. But it's easy to go in the other direction in this case, and it turns out that that's pretty common. There are lots of domains where it's sort of easy to calculate conditional probabilities in one direction, but not in the other. And again, it's not that hard to have sort of a prior belief or a prior probability over just if I pick someone off the street, what's the probability that they'll have a cough? And I can also have a pretty good idea of what's the sort of prior probability that some random person picked off the street will have pneumonia, right? I can look in medical databases to sort of figure out estimates for all of these things. And if I have those estimates, I can just plug them into Bayes' rule, and I get my diagnosis, right? I get my probability that patient has pneumonia. In this case, it's 0.5 times 0.001 divided by 0.1, it gives me 0.5. So when people talk about Bayesian inference or Bayesian reasoning, one thing that they're often talking about, that they often have in mind, is this notion that when we're deciding what the probability of something is, we're taking seriously the prior probability that we believe that thing might be true. So in this case, even though people who have pneumonias very frequently do have a cough, and this person that we're observing, right, they have a cough, there's still a very small probability that this patient has pneumonia just because pneumonia is pretty rare, right? So Bayes' rule allows us to take that into consideration, that prior probability of something being true into consideration. Which, probabilistically speaking, is the right thing to do because this identity is correct. Right, so sometimes it seems tricky to know what the probability of the evidence is. What's the probability that we're going to see some evidence? So it turns out that we actually don't need that. We can calculate that from the other terms if we have to. And we often don't care. Right? If we have several different hypotheses that we're trying to decide, right, does this person have pneumonia, or do they have lung cancer, or are they perfectly healthy? Given a particular piece of evidence, right, given the fact that that person is coughing, the denominator here is going to be the same for every one of those hypotheses, right? The probability of the hypothesis doesn't show up at all down here. So if we just get rid of this thing, we'll get some number that's proportional to the probability of the different possible diseases or the different possible diagnoses. They won't be probabilities anymore because we'll have sort of thrown out the bottom, but the biggest one will be the most probable. So if we only care about finding the most probable hypothesis, we can usually actually just throw away the denominator. And even if we don't throw away the denominator, we can sort of recalculate the denominator by using this identity. The probability of the evidence is equal to the sum over every possible hypothesis of the probability of the evidence given the hypothesis times the probability of the hypothesis. And again, this is just an identity. It's demonstrated in the textbook, I believe. And it's not surprising, right? Because we know that this probability has to sum to 1 over all of the possible hypotheses. Adding up adding this term up for every possible hypothesis and putting it on the bottom ensures that this thing will sum to 1. So that's one way of thinking about it as well. Okay, so that's 90% of what we need to know to do probabilistic inference in AI. That's the foundation. I think next time we'll look at how to actually apply that to some more interesting problems.